You hear it everywhere, right? AI, big data, machine learning. We talk about these incredible algorithms that can predict what movie you'll like or how the stock market will move. But before any of that magic happens, there's this hidden first step. It's a step that can eat up, get this, nearly 80% of a data scientist's time, but you almost never hear about it. Well, today we're pulling back the curtain.
Okay, this phrase right here, this is the one law you can't break in data science. Garbage in, garbage out. It's that simple. It means if your data is a mess, your results will be a mess. You can have the most powerful, brilliant AI in the world, but if you feed it junk, you're going to get junk back. So where does all this garbage come from anyway?
Well, it comes from the real world, because real-world data is, well, it's messy. It's not some perfect, tidy spreadsheet. It's more like a chaotic, noisy room filled with missing bits, human mistakes, stuff written in weird formats, and a whole lot of clutter. To find any actual truth, you've got to roll up your sleeves and bring some order to that chaos.
You know, the best way to think about a raw data set is to picture it as a crime scene. Seriously, it's a total jumble. You've got confusing clues all over the place, some false leads, and critical pieces of evidence are just gone. You can't just walk in, point, and solve the case. Nope, you need to call in a detective.
And what makes this particular crime scene so tricky? Well, for starters, you've got missing values. That's like your star witness vanishing. Then you have outliers. These are the really suspicious clues that just don't fit the rest of the story. You've got inconsistent formatting, which is like finding notes written in a dozen different secret codes. And of course, duplicate records, which is like finding the same fingerprint copied and pasted all over the room, totally skewing your investigation.
So, who do you call to make sense of this data crime? You call in the expert, Exploratory Data Analysis, or just EDA for short. EDA is our detective. It's the process that shows up at this chaotic scene, ready to organize the evidence, question the witnesses, and find the real story hiding underneath all that noise.
Now, this isn't a newfangled idea. It was pioneered by a brilliant mathematician, John Tukey, way back in the 1970s. The whole idea behind EDA is simple. You investigate the data before you do anything else with it. It's about getting to know your data, learning its personality, finding its weird quirks, and spotting problems, a lot of the time just by creating simple charts and pictures. And every good detective has a plan. EDA's investigation follows 4 basic steps. First, you inspect and clean the scene. Get rid of the mess. Second, you question each witness, each variable, one by one. Then you start looking for connections between their stories. And finally, you get the case file ready for court, which in our world means getting it ready for a machine learning model. The very first job is to secure the crime scene. This is absolutely critical. It means cleaning up all that messy data we talked about. We've got to deal with the missing clues, the strange-looking evidence, and the information that's just repeated over and over before we can even hope to understand what really happened. So our detective runs into their first big problem right away. What do you do when a key piece of evidence is just gone? How do you handle those empty spaces, those missing values in your data? You've really got 2 main strategies. The first is called deletion. It's the quick and dirty method. You just throw out any case file that has information missing. But the risk is huge. You could be throwing away a ton of other valuable clues along with it. The second, more thoughtful approach is imputation. Here, you make an educated guess. You look at all the other data you have and fill in the blank with a logical value, like the average. It keeps your evidence pile bigger, but you have to be careful. Okay, once the missing clues are dealt with, our detective starts looking for evidence that just feels weird. The clues that stick out. These are called outliers. Data points so extreme that they seem suspicious. Maybe it's a typo, or maybe it's a sign of something truly unusual going on. And one of the detective's favorite tools for this is the box plot. It's a super handy chart that gives you a quick snapshot of your data. See that main box in the middle? That's where most of your clues are. And those little dots way outside the lines or whiskers? Bingo. Those are your suspicious outliers flagged for a closer look. So why are we so obsessed with these outliers? Because they're troublemakers.
They can completely distort the story your data's trying to tell. A single crazy number can drag the average way up or down, making your summary totally misleading. And when you try to train an AI model, outliers just confuse it, which leads to models that make bad, inaccurate predictions. All right, so the scene is clean and secure. Now the real investigation can start. It's time to question the witnesses. In our data world, the witnesses are just the different variables. We need to look at each one by itself and then start looking for how their stories connect. The investigation starts with something called univariate analysis. Now, uni just means one, so we're simply looking at one variable at a time. We want to understand the story of each individual piece of evidence before we try to link it to anything else. What does it look like on its own?
A classic tool for this is a histogram. This chart just shows us the shape of a single variable. So if we were looking at commute times, for example, a histogram would instantly show us the most common commute time, how spread out all the times are, and if the pattern looks normal or lopsided.
So after interviewing each witness alone, the detective starts pairing them up. This is bivariate analysis. Bi means two. And a scatter plot is perfect for this. You put two variables on a chart and just see if a pattern pops out. And here, it's pretty clear. As a driver's age goes up, the distance from which they can read a sign tends to go down. We found a relationship, a clue.
And finally, the detective brings it all together with multivariate analysis. That's looking at lots of variables at once. This is where you see the whole complex picture. It's like standing back from a corkboard with all the pictures and strings connecting them, seeing how everything interacts to tell the complete story.
Okay, the investigation is done, the story is much clearer. But now there's one last critical phase. Our detective has to prepare the final case file for court. In other words, getting all this clean, organized data ready for the machine learning algorithms to process. But there's a last-minute translation problem. The jury, our machine learning model, doesn't speak English. It only speaks one language: numbers. So what do you do with evidence that comes in as words, like male or female? How do we translate that for the court? The answer is a process called categorical encoding. It's basically a translation service. It's the essential step where we methodically convert all those text-based categories into numbers that our algorithms can actually understand and work with. And the process itself is pretty simple, but it's absolutely essential. A column that has words like male and female gets transformed into a column of numbers like 0 and 1. And just like that, the machine can read the evidence. The case is ready for trial. So after all that, the cleaning, the investigating, the translating, you might be asking, what's the big payoff? Well, the payoff is everything. It's the difference between an AI that works and one that's a total failure. Doing this right prevents you from making bad decisions based on flawed models. It ensures your analysis is based on the real story in the data, not just the noise. It is, no exaggeration, the bedrock of all good, reliable data science. We always hear that phrase, data is the new oil. But let's think about that. Crude oil, straight from the ground, is just thick, messy gunk. It's not useful until it goes through a refinery. It has to be explored, processed, and refined before it can actually power anything. Which leaves us with a final thought. If data is the new oil, then maybe, just maybe, EDA is the refinery, that crucial hidden step that unlocks all of its true power and value.